The objective today is to explain what the Intel manual says about denormal operand exceptions. And as you can see here, it's pretty short, so I'm going to rely on Wikipedia after going over the Intel manual part, just to give the video some maybe more beef to it. I just feel a little guilty if I make really short ones. Well, the processor reports the denormal operand exception if an arithmetic instruction attempts to operate on a denormal operand. So this is pre-computation, people. Now, we did read about normalized and denormalized finite numbers, but clearly when there's a denormal one, there's going to be an exception flag triggered. When the exception is masked, the processor sets the DE flag and proceeds with the instruction. Operating on denormal numbers will produce results at least as good as and often better than what can be attained when denormal numbers are flushed to zero. So let's start with the question, what is a denormal number? And I'm going to answer that several times in the video. So if you don't know it yet, just hold tight. But the second question should be, what is flushed to zero? And I think that's the first time we are reading those words here in the manual. So let's also table this question just for a future answer. Well, programmers can mask this exception so that a computation may proceed, then analyze any loss of accuracy when the final result is delivered. When a denormal operand exception is not masked, the DE flag is set, a software exception handler is invoked, and the operands remain unaltered. When denormal operands have reduced significance due to loss of low order bits, it may be advisable to not operate on them. So essentially what it's saying here is if the number is really that tiny, you might not want to operate on it, and so therefore you can think about that as a programmer. You can unmask the control word of the x87 FPU, or at least that bit that handles this denormal operand exception. So if you were to unmask that control word, what will happen is those operands will remain unaltered, and thus there will be no result. So the full question is, what happens when you unmask the DM of the x87 control word? And remember, DM should just stand for denormal mask. So here on page 105, this is the part where it talks about the control word holding the mask bits. And right here is the name of all those masking bits that correspond with, obviously, these flags. So that's page 105, just for your reference there. Now, precluding denormal operands from computations can be accomplished by an exception handler that responds to unmasked denormal operand exceptions. So you can create this exception handler either in the operating system. You can have operating system exception handlers, or you can have exception handlers in the software you're writing. Now, Intel will tell you to see the following sections to learn more about this stuff. We'll eventually get there, but for now in this video, I want to take you to a Wikipedia article. It's a pretty good one about denormal numbers, so we're just going to kind of hammer away at that definition. Now, on Stack Overflow, I see people using the term subnormal numbers, and at least my experience, they just seem to use that more than the term denormal. Though personally, I'm preferring denormal. And I guess the reason why is just because the Intel manual uses it. Well, here on Wikipedia, it says that denormal numbers fill the underflow gap around 0 in floating point arithmetic. So that's just kind of a fancy way of saying it takes the area between 0 and really tiny numbers. It just takes care of that area. So when they say underflow, similar to overflow, an underflow occurs when a number is so small that there aren't enough bits to represent how small it is. So you could think of several hundred decimal places that such a number would try to utilize to represent a very tiny number. So any non-zero number with magnitude smaller than the smallest normal number is thus subnormal. Now, in a normal floating point value, there are no leading zeros in the significand. And so we've gone over that by saying that there's a 1 that is implied at the beginning of the significand. What they go on to say here, though, is instead leading zeros are removed by adjusting the exponent. So I'm a little confused, but great thing they have an example. So for example, 0.0123 would be written as 1.23 times 10 to the negative 2. So sure, the exponent tells us where to move that decimal, right? And then we're not going to have like leading zeros to the left of the decimal. Just like we wouldn't have, would they call it trailing zeros on this side? Either way, we don't want to put zeros when we don't have to. It's a waste of space. So these denormal numbers are numbers where this representation would result in an exponent that is below the smallest representable exponent. So this part's a little confusing. Let's jump to notice for a binary radix, and a radix is that point. It's a binary point for us. Over here, since they were working with base 10, it's a decimal point, right? Decimal, deca for 10, bi for 2. So notice that for a binary point, the leading binary digit is always 1. I literally just said that. Now, in a denormal number, since the exponent is the least that it can be, 0 is the leading significant digit. That's a little mind-blowing right there. So a simple way to answer number 1, what is a denormal number? You could say something like, is a number where the implied one of the significant or significand, I've seen it both ways, becomes 0. Or you could say like that implied one just disappears. All because the denormal flag is set. And by doing that, we're allowing the representation of numbers closer to 0 than the smallest normal number. They go on to say a floating point number may be recognized as denormal whenever its exponent is the least value possible. So what's the smallest number you can have in an 8-bit number? The answer is 0. So that exponent would be all zeros. So a good check for understanding is why can't we make a normal number? See, the keyword is normal right there. A normal floating point number. Why can't we make one with an exponent of negative 127? And the answer is because as soon as we make a number, whether it's positive or negative, okay, let's go with positive. So as soon as we make a number, all zeros, so there's 8 zeros right there. Let me move that down so you can see it better. So as soon as you see these 8 bits are all zeros, all the numbers in the significand over here, whatever they may be, and in single precision we would go down to 23 bits there. As soon as you see these all are 0, we are now looking at a denormal number. That's like the sign for the denormal number. So thank you Wikipedia for just giving us some really good insight right there. Now I'm positive Intel does say that in one of the tables. I want to guess table 4-10, but not totally sure. But let's just finish up this introduction here and then we'll call it good. So by filling the underflow gap like this, significant digits are lost, but not as abruptly as when using the flush to 0 on an underflow approach. And here's our answer to question number 2. Discarding all significant digits when an underflow is reached. So what happens in a flush to 0? Discarding all significant digits. So a flush to 0 may have this scenario where the 1 is still implied, okay? There we go. So if the 1 is still implied and we do a flush to 0, all of these significant bits just become all 0. So actually, why don't we do this? I'm going to leave my example of the denormal number. And here's my example of a flush to 0 scenario. They go on to say, hence the production of a denormal number is sometimes called gradual underflow. So this might not be a very good question, but at least we'll make these connections. What's another name for a denormal number? Another name could be a gradual underflow. Oh, right here brings some clarity. It looks like in the IEEE 754 standard in 2008, denormal numbers were renamed subnormal numbers. So who do I choose, the IEEE or the Intel? Or do I just look extra smart by knowing both? Well, they are supported in both binary and decimal formats, and in binary interchange formats, subnormal numbers are encoded with a biased exponent of 0. But are interpreted with the value of the smallest allowed exponent, which is 1 greater, that is, as if it were encoded as a 1. So I think it's example time. Let's say I had my 23 bits. So there's 1, Okay, and 23 or 22 zeros. Now there's no implied 1 here, so I could put a 0, but I'm just going to leave it. I just know that radix is right there. Okay, so now let's say we have negative 127, so I need to move that decimal negative 127 times. And which direction am I doing that? Well, since it's negative, it's this way. So I could, wow. Let me get rid of all these now. And basically, if I was just to keep going, that's how we get to the negative 127. So I guess my question here is, what happens next? Is there just that one number that it can represent? From memory, I remember reading that the 754 standard can go to negative 128 and 129, etc. And I don't know how they're doing that. And before I start scrolling down, showing you where I found my answer, let me just point out that in decimal interchange formats, they require no special encoding because the format supports unnormalized numbers directly. So the point is, when you try to send this over the wire through an interchange using the 754 standard, everything's fine, so don't worry about it. Okay, so here's where I realized I went wrong. I started with that one all the way right next to the decimal. Okay, so when I have a denormal number, all right, just like that, this number is going to be a binary number to the negative 127. But if I just moved it 1 and represented those bits, okay, I'm going to have to set up my significand all over again here. So I need 23 total bits for my significand. Okay, so there's 23. So if I start the 1 here, then in a denormal number, I'm to the point where I'm at negative 128. If I move it over 1, I'm at 129, and I could keep going until what? So what is the smallest number a denormal number can represent? Now to cheat a little, I did search for negative 146 in the Intel manual, and apparently that doesn't exist. I'm going to have to go to Stack Overflow to double check, but for everybody out there watching this, here's my guess as to the answer to my own question. Make sure you double check your answer, maybe even in the comments below. So, as always, thank you for watching, and next time we'll look at the divide by 0 exception, and I'll probably confuse you more than I ever have before, because not only did I get the number wrong in the beginning of that video, but I also have a heck of a time with this sentence right here. But the good news is I did find solutions, so when you get to part 40, I'll go ahead and clarify what I found.